Okay, let's get started. Hopefully you're writing your instructions for first milestone. Everything going fine with that? Okay. All right, so let's get back to lecture then. We are working our way through our second lecture on collective robotics, and the basic idea here is thinking about how to evolve coordination strategies so we could have a swarm of robots do something that is difficult or impossible for any one robot to do on its own. As whatever the collective task is that we want our swarm to perform, as that task becomes more complex, usually there is a greater need for specialization and coordination and ultimately signaling. So if we're going to coordinate as a group, you need to know what I'm doing so you know what you're supposed to be doing. If it's not immediately clear from watching me what I'm doing, I can communicate with you. Right? So language obviously evolved as a tool to allow groups to coordinate on a larger and larger scale. So we're going to jump back to lecture 23 in a moment. We were actually looking at a relatively simple experiment where they actually evolved communication. But as we started to see last time in lecture 23, there's something that's particularly challenging about evolving communication above and beyond all the other aspects of cognition that we've seen evolved in this class. What is particularly challenging about the evolution of communication? We know why it's useful, so it allows a group to coordinate, but how does it get started in the first place? Yep.
Is there to be some sort of like mutual language between the two things that communicate?
Absolutely, right? So in order for communication to work, you need to have the speaker or the signaler give the right signal or the right communication in the right circumstances. And you need to have a listener who is able to hear that language or that command or that signal and do the right thing when he or she hears it, right? If you're missing either of those, if the speaker is not communicating properly or the listener is not understanding properly, then obviously the language can't get started, right? So evolution of communication is difficult because you need speakers and listeners to evolve at the same time. Okay, so back to lecture 23. Just to remind you what we're looking at here, this is a pretty old paper in the field. They were evolving communication for agents that existed in this grid world. At any one time, any given agent could occupy a single cell of this grid. This is somewhat different from what we've seen before because now we have male and female agents. And in this experiment, the females are deaf and immobile, but they can signal, so they are the emitters of language. Males are blind, they can hear, they cannot signal, but they are mobile. And the fitness here is for a male to move to find a female. And what is going to be evolved here is not just how the males move, but what signal is produced by the female when she detects a male entering her zone of sensation, where she can hear or she can sense a male approaching. So we're going to evolve movement strategies for the males, we're going to evolve signaling strategies for the females, and finally we're going to evolve the ability of the male to change his behavior based on what he hears from the female. Okay. We looked at the neural networks for the male and female agents in this experiment last time. So the females take as input to the neural network information about where a male is in her local environment, if there is a male there, otherwise it's all zeros. Propagate signals through the neural network, and the output layer of a female network is the song that she emits. If there are any males that are that are close by, the males receive that song or that signal, if you like, as input. So the males hear the song, and then the output layer dictates how the male moves in response to the song. Right? If a male and female move if a male moves onto the same cell as a female, they produce one male offspring and one female offspring. The male offspring is a mutated copy of the male, and the female offspring is a mutated copy of the female. Those two new male and female agents overwrite some other male and female agent in the grid, and the male and female parents are moved to random empty positions in the grid. So a male that is able to rapidly find and move on to the same cell as a female produces a lot of offspring, and a female that emits a song that causes a male to find her, she also produces a lot of offspring. Right? Okay. So we looked at one experiment last time where the males start by moving at random, and they very rapidly, the males evolve the ability to move forward. Why did they evolve the ability to move forward? It's better than staying still, right? If you stand still or turn on the spot, by definition, you're not going to find a female. Best thing to do is just move forward. After 15,000 time steps in the simulation, some males have now started to respond to song 101 and song 110. Otherwise, the males just move straight. So something is happening here. And we looked at what was evolving in this particular run, which was females started to evolve a song that they would emit whenever they detected a male had landed on the same column or the same row as the female. And she would emit the song that causes the male to turn. And when the male turns and is now facing towards her, she emits one of those other 6 songs, and the males do what the males usually do, which is just move forward. Right? So in essence, the song is stop moving forward and turn, and that song is emitted when the males are on the same row or the same column as the females. Okay, we looked at this last time. I won't go through this. Here's a little cartoon showing how this works. Here's the female here. She's emitting a song that causes the male to just move forward, or the male is ignoring the song at this point. The male is moving forward, and when the male reaches this row, the female changes the song to 011, which causes the male to turn 90 degrees to the right and find the female. Here's an example later in that evolutionary run when the female is now able to emit calls and capture males that are coming in from any of the 4 quadrants relative to herself. So now the male is coming in from above, and she emits the song that causes the male to turn to the left. She continues to emit that song, so the male makes 3 left turns and is now facing the female and approaches the female. Right? So in essence, at this point in evolution, the female is widening her net and figuring out that there are more conditions under which she can emit this song and attract the male. Okay. So that's evidence that in this simple experiment, communication will evolve, and it evolves despite this trickiness of having the female having to emit the song at just the right time, and the male being able to interpret that song correctly. Barry.
So going back to what you were asking at the beginning of class,
yes.
you need some kind of neutral language. All of a sudden I'm confused. Does it require that the designer of the system understand the language they're both going to speak from the get-go, or is it actually something that will naturally evolve, that, you know, if the female does this thing with this song, that male will come along, and those of the males that respond appropriately by turning will evolve, whereas others who
do something
that,
else when they hear that
song just die off.
That's exactly it, right? So to reinterpret your question, the question is, did the investigators who set up this experiment have an idea about what the language should be?
Yeah, here's a common language, and we've got our 2 pools of males
That's
and
it.
females, so we'll have them.
So that's what's exciting about this paper is they did not do that. They did not build the language in beforehand. They did not presumably have a preconception about what that language would be. The language itself evolved. The fact that this particular song, not that song, the one before it, that this particular song, 101, causes a significant fraction of the males in the population to turn left whenever they hear it, that's just an accident of evolutionary history. There was one or a few males at some point during this simulation that when they received 101 as input, they turned to the left. Now it turns out that at least some of those males must have turned left at just the right time, which in this case would mean they turned left so that they were facing the female. And by chance, the female would stop emitting this song 101 when she detects that now there is a male that's facing her.
Right, so similar to the Twitch thing where they learn what certain inputs from the audience indicate.
Similar. So the Twitch Plays Robotics project, that was the crowd teaching the robots language, right?
Jump, jump, jump.
That's
and
it.
After a while, the right ones
Would start to, that's right. So that's the idea here. Now the females, remember the females are really nothing more than just a very simple neural network, right? So the females don't know much, they just know, or the neural network knows that when there's a certain combinations and ones of zeros up here, produce ones and zeros down here. The ones and zeros up here represent there's a male to the north of me, and that male is facing south. That's good news, right? That means if the male continues to move forward, the male will find this female. That's it. There just happened to be a female that had emitted a particular song that caused a male to turn towards her, and she also happened to stop singing that song when the male was facing her, and the male also happened to stop turning when the male stopped hearing that song and moved forward, right? That chance event led to a few males and a few females finding each other at a slightly higher frequency than the other males that were just moving forward or were turning to the right instead of the left when they heard this particular song.
She continues on the voice.
Yes, that's right. Exactly. Just by chance, right? And once that happens, once these males and females start to find each other at slightly higher frequency, remember that they're producing mutated copies of each other, which means the female child is likely to emit the same songs as her mother under the same circumstances, and the male child is likely to respond to particular songs in the same way as his father, which means those males and females are going to find each other more often, and so on, right? You get a positive feedback loop, and as long as that set of fortuitous circumstances arises, it starts to reinforce itself, and you get more and more males in the population that are responding to this song, and more females that are emitting this song, and you have the evolution of communication. Make sense?
What happens when there's more than one male within that sensory region? So there could be more than one input.
Yep. So what happens when there's more than one male in a female zone? So these two males will hear this female song. But now that I say that, this male is in both female zone. I don't know how the investigators dealt with that situation. The males would hear this female song, and the female detected the position and orientation of the male that was closest to her. So the female can actually only see, quote unquote, the closest male, but all of the males in her radius of singing could hear that song. I don't know how they dealt with the situation where a male can hear two females. Okay. So we ended last time with this slide. So now we're going to look in a little, the investigators looked in a little more detail at how exactly this language evolved. So what we just saw in the previous slides is the fact that language does evolve. And it evolves so that females can attract males and produce more offspring, which means there's more offspring that understand and speak that language, and it takes over the population. How exactly does that happen? Well, the way they did it was to reduce the output layer of the females to just 2 output neurons. So now the female can only emit one of 4 songs, 0, 0, 0, 1, 1, 0, and 1, 1. Sorry, I'll go back to the 2 neural networks here. So now the output layer of the female only has 2 output neurons, and the input layer of the males also have only 2 input neurons. So they've reduced the number of possible songs that the female can sing. And remember that the males can do 1 of 4 actions. 0, stay still, 1, go forward, 2, turn left, and 3, turn right. By simplifying things in this way, they can create this entire table, and this one table here shows exactly what every male in the population is doing at this point in time. So this is at the beginning, time equals 0 at the top of the table here. So this is the beginning of the simulation. Random female neural net, 800 random female neural networks and 800 random male neural networks. If we look up here, there are 4 males that 0 stay still in each of the 4 cases. There should actually be 4 zeros here. So in all 4 of the songs, there are 4 males that just stay still no matter what. Here, in this case, there are 6 males that stay still if they hear one of the first 3 songs. But if these 6 males hear the 4th song, which is 1, 1, what do those 6 males do? They go forward, right? So you can actually see there are groups of males here that do all sorts of things. Down here, there are 6 males that turn right, no matter which of the 4 songs they hear. So far, so good? So we can see at a glance what all of the 800 males are doing. Okay, so as you would expect at the beginning, they're random, so they're doing all sorts of things. This is after 8,000 time steps. You can see that most species, quote unquote, if you like, of males have died off. So most of them are 0. And there are groups of males that are evolving to do certain things. So there are 92 males now over here that go forward most of the time, but turn left if they hear the 4th song. That sounds familiar, right? That's like the males that we saw a few slides back. At this point, however, the largest group was this group here. There were 547 males that went forward most of the time, but turned right when they heard the 2nd song. And it turns out that these males were responding to females that only emitted songs 1 and 2. So remember that this table is showing us the males, it's not showing us the females. So at this point, there were females that were emitting songs 1 and 2 at the right time that would attract these 547 males. So far, so good. 2,000 time steps later, at time step 10,000, there's another group over here, and this group of males is acting similarly to this group. They're going forward most of the time, but they're turning right when they hear song 4. And it turns out that these males are able to find a certain group of females that are only producing songs 3 and 4. So behind the scenes, there are 2 groups of females. One group that's emitting songs 1 and 2, and another group of females that's emitting songs 3 and 4. And those 2 groups of females are attracting, the first group is attracting this group of males, the second group of females is attracting this group of males. What's happening?
Populations are diverging.
They're diverging, but in what way? Can we be more specific? They're diverging in what way? What's happening?
They're learning 2 different languages.
They're learning two different languages, right? So now this isn't the evolution of language, this is the evolution of languages. Again, the investigators did not put this in a priori. It just happened that in this case, that fortuitous set of circumstances that we just talked about happened twice, and those two independent events got locked in, right? It was the beginning of two languages.
How do you know only signals 3 and 4?
Again, that's not shown here, but that was something that the investigators looked into. So they looked at all these males, and they looked at the females that they found, and they found that those females only ever emitted song 00 and 01. And 127 males in the other group always found females, and those females only emitted songs 3 and 4. Okay. If you were an enterprising male in this world, what would you do? Learn both languages, right? Which group here? So we've got one group of monolinguists down here, another group of monolinguists up here. Where are the bilingualists? 321. Not quite, because you'll notice that these males go forward and turn to the left when they hear the second song. And you should not turn left when you hear the second song, because the females that emit song number 2 are telling the males turn right. Because if you turn right, you find the female. So if you do 1, 2 when you hear, if you do 2, if you turn left when you hear that song, you're probably not going to find the female. She may continue to sing the song. It's not clear from here, but probably not.
It's the 20-1-3-1-3.
There's only 20 of them so far, right? They're in the minority, right? This group of males here have 1-3, so they're doing the right thing. These males are doing the right thing when they hear songs 1 and 2. And they also do the right thing when they hear songs 3 and 4. So presumably, there are very few of them, but if any of those happen to come into the range of the first group of females or the second group of females, they will find them. This group will only be able to find females in the first group because 1-1, they'll go past females from the second group and vice versa over here. Okay, so let's run this simulation forward to 12,000. So there we go, right? We've gone from 20 bilingualists to 128. Let's keep going. Time step 14,000. Now we have 217 bilingualists. At time step 16,155 bilingualists. 517, 1,140, and finally 1,600. I misspoke, right? So there's, in the original experiment, there was 800 males and 800 females. Here there were 1,600 males and 1,600 females. Okay, so the American males among us who only speak one language, take a page from the agents in the Werner and Dyer paper here, right? Okay, so that concludes our discussion about the evolution of communication. A lot of interesting work still to be done in this area. Again, for roboticists, aside from the interesting sort of biological analogies here, where you could actually use this experiment to study how languages evolved in animal groups, this is probably important for roboticists as well. We want to create large robot teams that work together. We want those robots to evolve their own language and be able to signal and coordinate on a larger scale. Any questions about these two lectures before we move on to evolving bodies and brains? Okay. All right, so we're now moving into the last theme of the course, which will take us up to the end of the course here. I mentioned this at the beginning of the course. Robotics is a huge field. There's lots of different approaches to robotics. In this course, we've been looking at just one particular approach to robotics, which is evolving robots. The main advantage of evolution over learning, and learning is used in a lot of other branches of robotics, is that evolution is not restricted to changes to the brain. Right? Learning, by definition, is synaptic plasticity or changes to the brain, but of course evolution did not just shape our nervous systems. Evolution shaped our body plans along with our nervous systems. Why does that matter? Well, again, at the beginning of the class, we talked about embodied cognition, right? One of the ways that we evolved and learned to survive and flourish in the real world is we can push against the world, literally or figuratively, and observe how the world pushes back. So by using evolution, evolution can carefully tune the relationship between body and brain to make it easier for robots to reach out into the world and learn about the world around them. If we build the robot body by hand and then evolve the brain, or use a learning algorithm to tune up the synaptic weights in a brain, perhaps the body that we designed by hand was not appropriate, right? So we want to allow evolution to make sure that these two important subsystems of any intelligent agent, body and brain, work well together. So in lectures 24 and 25, we're going to look at some experiments that actually do evolve body and brain. We've seen a few examples of that already as we've gone. And towards the end, lectures 26 and 27, we're going to see some experiments that show why you would want to do that. We're going to look at some experiments that are broken into two variants. In one variant, we evolve body and brain and see how well the robots do. And in the other case, we only evolve the brain but fix the body. And if this first experiment does better than the second one, why? What is it about the evolved body and brain that allows these robots to do better than the robots where we build the body by hand and then optimize just the brain? Make sense? Okay, so let's start with the first attempt to do this, which was done by Karl back in 1994. So again, this was a relatively old experiment, over 20 years old now. Most people in the field agree this is still one of the high water marks. This was one of the most famous experiments in evolutionary robotics. I'm going to start today by playing the video for you, and you'll probably see why it became so famous.
This demonstration shows virtual creatures that were evolved to perform specific tasks in simulated physical.
Let me see if I can get the audio for this.
Creatures that were evolved to perform specific tasks in simulated physical environments.
Okay.
Creatures that were evolved.
Sorry? Okay, let's try this again.
This demonstration shows virtual creatures that were evolved to perform specific tasks in simulated physical environments. Swimming speed was used to determine survival. Most of the creatures are results from independent evolutions. Some developed strategies similar to those in real life. Once they're evolved, multiple copies of these creatures can be made and simulated together in the same environment. The next group of creatures were evolved for their ability to move on a simulated land environment with gravity and friction. Some simple solutions with just two parts were found. Some seemed like they could use some assistance, while others were fairly efficient, such as this rowing-like behavior. Here is an odd cousin of the previous. A mutation caused him to tumble. Some creatures evolved to incorporate contact sensors in their control systems. Here is another inchworm-like creature that tends to go in circles. This was actually a creature first evolved for its ability to swim in water, then later put on land and evolved further. A successful sidewinding ability resulted. Here is one with a hopping style. The protrusions on its arms seemed to help prevent it from tipping over. This was the fastest, with a successful galloping-like stride. This group was evolved for their jumping ability. This group was evolved for their ability to adaptively follow a red light source. The resulting creatures are now being interacted with. A user is moving the light source around as the creature behaves. This one seems to flail randomly, but somehow still manages to approach the light. Perhaps it is mean to move the goal away just as it arrives. Here is one that has propeller-like fins which are tilted depending on the direction of the light. It can adaptively swim up or down very well. This final group of creatures was evolved for their ability to compete for control of a green cube. The creature closest to the cube at the end of a simulation is the winner. Here, a strategy first arose for simply tumbling towards the cube. Then one learned to block out his opponent. But then later, one learned to overcome the obstacle by climbing over it. Some pinned down their opponents. Some covered the cube with protective arms. Others simply unfolded onto the cube. The success of a strategy is often highly dependent on the opponent. Here is a hockey-playing creature, which takes the cube away and wins by a large margin. Here are two similar hockey strategies battling it out, with appropriate gestures. This crab-like creature walks well, but often continues past the cube and instead seems to prefer beating up on his opponent. Against the arm, the crab seems to simply walk away. A successful strategy is this two-arm technique that swipes quickly in from the side and moves the cube over to a second arm. These are the final rounds of competition amongst the overall best. Finally, the seeker arm goes against the side swiper, but the cube is just out of reach.
Not bad for 1994. Okay, so we just mentioned that one of the goals of using evolution in robotics is to evolve body and brain together. And often, like in nature, evolution can find a solution of a relatively simple body plan combined with a relatively simple controller to get the job done. There were a number of examples of that kind of exploitation in this video. What were some of those examples? What were aspects of the body that allowed, presumably, a pretty simple controller to lead to successful behavior? Symmetry. Okay, we saw a lot of examples of that. Why is symmetry useful in some of these tasks here?
With the two arms, it allows it to kind of wrap around the cube.
Absolutely, right? So it probably evolved this left arm, and through some symmetry, you get grasping, so that was relatively easy. What else? Symmetry also helped for the robot that was evolved for phototaxis, or moving towards the light, right? There was one that had the twisting fins on the top and the bottom. Pretty simple, as long as the light is usually above or below you, you just change the spin of the top or the bottom fin, or the relative rate of spin, it'll take you up and down. Pretty simple, right? If you had a different body plan, you might have to actually turn around and then head in a forward direction. Right? That body plan allowed that robot not to have to turn around when it was moving in different directions. Other examples? So in the case where the robots were evolved for jumping, you could see one that sort of twisted around and then jumped on the spot, right? It sort of was evolving almost like a whip appendage. So it was relying on momentum to throw itself in the ground, up in the air, rather than evolving some complex pair of legs that would allow it to jump in the air. So some pretty simple examples, but again, you could see that already evolution is starting to exploit the body plan of these robots to get the job done. Okay, so let's have a look at how this was actually done. As I mentioned, this was done back in 1994, pretty impressive for that time. Again, no physics engines existed at that time, except for the one that Karl wrote himself for the express purpose of doing these experiments. Pretty impressive. Okay. He had some pretty heavy hardware behind him at the time. Sims actually carried this work out on the connection machine. Anybody remember the connection machines? This was a while back. The CM5 that he actually used made an appearance in Jurassic Park there. That's very, very distinctive red lights and banks of computers here. That's the Connection 5. The red text on the right, I apologize. The text that's on your slide describes CM2, I think. Sims was actually using CM5. The connection machine, as the name implies, was pretty exciting at the time because it was a supercomputer that was highly parallel. So there were a number of cores, and those cores were connected in a hypercube topology. So if this is one core, this is another one. We could connect these cores together. They could share information and do parallel computation. If we have 4 cores, we could attach them together like this. If we had 8 cores, we could attach them together in a cube. If we had 16 cores, we could attach them together in a hypercube. And if you work your way up to 124 cores, they were all connected in this hypercube way. So a lot of parallel computation here, which is perfect if you're trying to simulate or evolve a population of 300 robots, right? You can execute the physics engine on each of these cores and then run them in parallel. The parallelism was done in such a way that it actually made a pretty powerful machine. It was clocked at about 131 gigaflops per second. The MacBook Pro, again, depending on how you run it today, is a little bit under that. So you can think of the CM5 as basically a MacBook Pro at the time. Not bad. Right? Okay. Okay. Let's have a look at the genotype to phenotype map for Sims's creatures here, right? So the genotype, again, is the set of instructions that evolution is modifying over time. The phenotype is the thing produced by that genotype, which in our case, the phenotype is the robot. Okay. The genotypes in this case are nested directed multigraphs, and we will break down each of those 3 properties of these graphs in a moment. So the genotype is a graph, and every graph is made up of a number of nodes and a number of edges. A multigraph is a graph where you can have multiple edges going from one node to another. Directed means that the edges themselves have direction. That's pretty straightforward. We'll see the nested part, the nested aspect of these genotype graphs in a moment. This genotype dictates not just the body plan of the creature, but also the controller that's inside the creature, and we'll see how that's done in a moment. The way in which these genotypes are translated into phenotypes is using a recursive algorithm. So we have not seen recursion used in a genotype to phenotype mapping before. But we'll see it used here, and you can sort of see already what the advantage of using recursion is. What is the advantage of using recursion in the genotype to phenotype map here? What kinds of body plans does it tend to produce? It was actually mentioned a few minutes back. They're symmetric, right? They can also be fractal. We'll see why the recursive genotype to phenotype mapping leads to symmetry and fractals in a moment. Okay. Let's dig down into the genotype a little bit more. Each node in the genotype graph specifies how to build a part of the body. And the edges represent how to connect the target node or the target object to the source object. So each of the nodes here have a number of labels or parameters, and those parameters are evolved. The first label on each node are the body part dimensions. So what is the length, width, and height of the part that's produced? Each node also encodes parameters about the joint. So when, for example, the head of this humanoid is created, it's going to be attached to the body by a hinge joint, and you've got the normal parameters there that specify what kind of joint it is. We can have a hinge joint like you've been using in the assignments, or a ball and socket joint like your shoulder. There's different kinds of joints. The joint limits, how far the joint can rotate, and a recursive limit, which we'll come back to in a moment. Let's talk about the edges for a moment. So the edges also have a number of labels or parameters associated with them, and those parameters are also under evolutionary control. When a node is visited in the genotype, when we're translating the genotype into the phenotype, we take all the labels in the node and we use that to construct a body part, like the body here. When we follow then an edge to a new node, which dictates how to build a different part, a bunch of the labels here on the edge represent changes in this object relative to this object. So when we build this object, it has a certain length, width, and height that's dictated by parameters in here. It also has a position, an x, y, and z. So when we follow the edge, there are three numbers here, delta x, delta y, and delta z, which tell us how to change position. There are then a number of other numbers that indicate how the orientation of this object is different relative to this one. In this case, these two objects have exactly the same orientation, so these parameters would be 0. There's also change in scale. So numbers here might dictate that this object is smaller or larger than this object. Okay. We also have additional flags in there like reflections, so perhaps we reflect across a particular axis of symmetry. Okay, so now we know how this works. We start by visiting one node in the genotype graph. We create that object in the physics engine. We follow all of the outgoing edges. And when we get to the new object, we create the new object relative based on the numbers associated with that edge. As I mentioned, these are multigraphs. When we're at the body here, we follow these 4 edges, which all tell us how to build this object here. But we're following 4 different edges which have different deltas. They have information about how this object, which is actually the same object, is placed relative to this object. So far, so good? Okay. You'll notice this has a self edge here. So we've just, for example, imagine we built the body. We follow this edge, and we've built the right upper arm. We follow this edge again, and this edge tells us that we're going to build a new object, which again is a limb segment. We're going to build this limb segment relative to the one that we just built, which was the upper arm. If we kept following this self-edge, we would keep adding limb segments on indefinitely, right? So if we're using this recursive approach, we need to have a base case or a recursive limit. So each one of these nodes has an additional integer associated with it called RL. Every time you leave a node, you decrement RL by 1. So when we get to this limb the first time, we follow this edge, RL is equal to 1. We build this. We follow the outgoing edge. We decrement RL, so now it's 0. We come back to this node. We create the lower arm. RL is now 0, so we do not follow the outgoing edges, which in this case there's just 1. What would happen if in this genotype everything was exactly the same, except instead of RL equal to 1 here, let's imagine a mutation event increases RL to 2. So we have this genotype, we make a copy of it, a mutation changes RL from 1 to 2, and now we create a second phenotype. What does that phenotype look like?
3-part legs.
It's going to have 3 parts, right? Each of these parts, there's going to be an upper, middle, and a lower arm. And RL is set to 2 for all of these 4 edges. So remember that these 4 edges dictate the upper arms and the lower arms. What would happen if instead we take this genotype, which produces this phenotype, again, we make a copy of this genotype, and a mutation adds a 5th edge? What's the phenotype we're going to get now?
You'll have an extra set of 2 arms connected coming out of the body somewhere.
That's right. There's going to be a 5th appendage attached to this body somewhere, right? Who knows what the parameters are. We have 3 arms and 2 legs, or 3 legs and 2 arms, depending on how the robot moves. Make sense? Okay. Let's have a look at this one. Oh, sorry. Again, if you look at this, you can see obviously how we get symmetry relatively easily. We have this reflection label down here, which often reflects objects across some plane of symmetry. Because we have recursion, it's relatively easy to also get fractal structures. So here in this genotype, we just have 1 node and 2 edges. This node dictates how to build this piece. We follow these 2 outgoing edges. So we follow them twice, which brings us back to the segment node twice, which builds these 2 pieces. For each of those 2 visits to that node, we again follow 2 outgoing edges, which produce these 2 pieces, and these 2 pieces, and so on. So what is the recursive limit here? Sorry?
Is there any at all?
There is if there was no recursive limit, what phenotype would you get?
Would it just keep going forever?
It'd just keep going, right? You have an infinitely branching tree. These 4, 5, something like that.
Oh, because of what result we see there.
Exactly.
Okay.
Okay, let's do the insect here, the hexapod. So we have one section here that builds this body segment. We then follow these 2 edges, which now produce this and this piece. So we visit leg segment twice, because we're following these 2 outgoing edges, produces this segment and this segment. We have 1 self edge, which comes back and adds another leg segment on top of the leg segment that was just created. We hit the recursive limit, we're done. We back up in the recursion, add another one here. There's a self edge here on body segment. So after we've built this body segment, we followed these 2 edges, built these 2 pieces, followed the self edge in both cases and produced these 2 pieces. We can follow this edge, which takes us back to body segment and produces another body segment here. We follow these edges all over again to produce this and this. So we're also getting hierarchy here. We have 3 segments, and each of those segments in turn is made up of 2 legs, and each of those legs in turn is made up of an upper and lower part. So one of the nice things about this genotype to phenotype mapping, like all of the other mappings we've talked about, is it tends to bias evolution towards certain kinds of phenotypes. You tend not to see random collections of rectangular solids in Sims's creatures. You tend to see things that are symmetric, hierarchical, and also in some cases fractal. And you get it because of this recursive property. If you look at animals and plants in nature, you also tend to not see animals that are random collections of parts. They tend to have symmetry and hierarchy and fractal structures because those things are useful for animals and plants. What is useful about symmetry? Why are most animals symmetric? Plants tend to be fractal, but not necessarily symmetric. Why is symmetry more important for animals than it is for plants? Movement? Okay, what is it about movement? That's true, right? So plants don't move. So there's some relationship between symmetry and movement. Yep. Momentum, okay.
Well, the same actions are basically performed on both sides of the body.
Both actions are performed on the same side of the body but flipped, right? Remember our discussion about legged locomotion. Whatever you do with your left foot, you're going to usually do with your right foot half a second later. If you think about it, if you have an animal that is asymmetric and that animal wants to move in a straight line, very difficult to do. You have to have an asymmetric gait. You're always going to have to compensate if you're asymmetric. So most higher animals are symmetric, and they're symmetric in the direction that they tend to travel, right? Which in our case is forward. Okay. So I've left all of the node labels and edge labels on the right for you here. And here's a collection of 12 phenotypes. What I'd like you to do is to turn to your neighbor and pick one or two of these and try and sketch out what would be the genotype that would produce that phenotype. Make sense? Okay. Turn to your neighbor. I'll give you a couple minutes, see what you came up with, and then we'll talk about them.
Like it probably started as one of the, started something like 7, 9, and then evolved to live off of it. Well, I think that this tail is a little bit
Looking at what it is.
you could just do like nose or getting edges and
Oh, I see. Create another leg here. And the bottom is the same thing, through sections, plus on each side.
We usually do the genotype to phenotype mapping, right? I'm making you do it the other way around, phenotype to genotype. Not so easy. Let's tackle some of the easier ones first. Let's try robot number 7 here. What would be a genotype for this one?
It's like a recursive column, so body, it's slightly weighted so that each recursive column will create a smaller box.
So how many nodes in this genotype? Probably just one, right? It's hard to, some of these are hard to tell, right? Is this last piece slightly different? Hard to say. But let's let's just assume there's one node for the moment called segment. And as you were mentioning, there might be a self-connection, and that self-connection, one of the labels for delta in size could be something like 0.9, which means create this segment first. We need a delta in position, so move to a new position, and now when you create the second segment, make it 9/10 the size of the one before, right? So move up a little bit, put this one here. This creature was probably captured while it was swimming, so maybe this wasn't actually the relative orientations. Maybe it was, hard to say. Okay.
So it just gradually diminishes until some
Until?
arbitrary limit you give it, like 0 or, well, that would be.
So the arbitrary limit would be RL, right? So the RL here is probably 7 or 8, right? Keep following that self edge and add smaller and smaller bits along the length until RL decrements to 0.
So until you get to your 7 or 8 pieces.
That's it, exactly, right? That's what happens when you're traveling through the genotype here, right? So RL equals 7. You create the first segment, follow this edge, and just before you follow this edge, decrement RL, create the next segment, decrement, and eventually get to 0, and you're done. Okay, 7's kind of easy. What else which other robots did you try and formulate a genotype for? 6, okay. So what do we need in the genotype for 6? How many nodes in the genotype graph?
Just 2.
2, okay, so let's call one B for body, and those look like fins. So let's call the second node F for fins. How are these nodes connected up?
There's a recursive call to body, and then
You mean a self connection?
self,
Yeah.
and then 2 to fin.
Looks good, right? So let's say we start here, we create one of the body segments, we follow these 2 edges, which places 2 fins on either side. We then follow the self edge, which produces the next body part along. We again follow the 2 outgoing edges and put fins on either side. Why are the fins placed 90 degrees rotated relative to these? There's something we need to add to this edge.
Position?
Not just position. So yes, the new body segment is going to be placed above the first body segment, but what else changes?
The orientation.
The orientation, right? So I'll just put delta O for change in orientation. So if we create the first body segment, we're going to place the second one just above, but when we do, we're also going to place it at 90 degrees relative to the first one, which means the fins are also going to be 90 degrees relative. When we add the third segment, it is also going to be rotated 90 degrees relative to the second segment, and so on. Yeah? Okay, let's move on. Some of these are a little trickier than others. We've been talking about the body so far, but we haven't said anything about the brain or the neural controller for these creatures. How was that done? Well, I mentioned that these are multigraphs, right? We can have multiple edges from one node to another. They're directed edges. They are also nested graphs, meaning that for every node in the genotype graph, there can be another graph that is nested inside each individual node in the graph. And even without explaining what all of these acronyms are here, you should probably be able to figure out what are the nodes and edges of the nested graph. What do they represent? So the nodes and edges in the top level graph, as we just talked about, dictate how to build the body, right? And what exactly about the brain do these nodes and edges represent?
How the body moves.
It's going to be how the body moves, right? We've seen lots of brains now that are made up of nodes and edges. What are those nodes and edges? Neurons and synapses, right? That's exactly what they are here. So going back to the creature we just talked about here, imagine that this node here creates this segment. When this segment is created, these three neurons are placed inside of it, and we'll come back to the synapses in a moment. When the two fins are added on to the main body, these 6 neurons are embedded in each of the fins. So this fin gets 6 neurons, and this fin also gets 6 neurons. Remember that when we're translating the genotype into the phenotype, we often visit these nodes more than once. Every time we do, and we're building a new body part, we put all of the neurons in there that are nested inside of that node. And then the edges here, not surprisingly, they indicate how to wire things up. I haven't mentioned the dotted node at the top. We'll talk about that one in a moment. So this embedded graph that's inside the top level graph describes the local neural circuitry for that body part. And in this case, Sims used a lot of the neurons that we've seen before. So this neural network is not organized into neat layers of sensor neurons, hidden neurons, and motor neurons. Those sorts of things are distributed all throughout the body. So here are 2 joint sensors, or what we've been calling proprioceptive sensors in this course. Each one of them gets 2, and we have 2 effector neurons here, which are our motor neurons. Everything else is hidden nodes. They mention contact sensors here and photosensors. In this example, there aren't any. You'll notice that when this fin is created, there are 2 joint sensors that are placed in here and 2 effectors. That's because in this case, the fin was attached with 2 hinge joints, one which can rotate the fin this way and one which can rotate the fin this way, which can produce this kind of motion. So this might be useful for some of you in your final projects. If you want to have this kind of motion, the easiest way to do it is to just attach 2 hinge joints together. So at every time step then, when this swimming creature is being simulated, the current angle of this hinge joint and the current angle of this hinge joint are being placed in J0 and J1. And the values arriving at E0 and E1 dictate the desired angle. E0 dictates the desired angle of this hinge joint, and E1 dictates the desired angle of the second hinge joint. Make sense? Okay. All right, so Sims also built into his hidden neurons a whole bunch of different activation functions, which we've seen before. So all of the neurons here always receive their input. So we always take the value of this neuron, multiply it by this weight. We add it to the value of whatever, this neuron that's coming in here times its weight. So we have that raw sum, and then we push that raw sum through one of these functions. So Sims allowed evolution to use a whole bunch of different kinds of activation functions. Some of these we've seen before. So the wave and the saw hidden neuron produce an oscillating signal, and the frequency of that oscillation is dictated by the raw sum. The larger the raw sum coming in, the faster the oscillation. The smaller the raw sum, the lower the frequency. Where have we seen that before? They were called something else when we saw them before. Neurons that always output an oscillating signal.
Is that the spinal column?
Yes, what's in the spinal column? What's in our spinal column?
CPG.
CPGs, which are central pattern generators, right? A lot of actions require an oscillation regardless of whether you're swimming or walking or running or cantering or what have you, right? Okay. Okay, the last one I forgot to mention, is it in here somewhere? This last, oh, it's right on the slide here, of course. Okay, non-local brain. So there's an additional node which is not turned into a body part, but that node can contain neurons there's only one copy of them, and those neurons can connect to different neurons in different parts of the body. So this is the non-local brain. There might be certain neural structure. There's only one copy of it. It sends out signals to different parts of the body, and those different parts of the body can also send signals back to the non-local brain. So every genotype graph has an additional node, and if evolution puts neurons and synapses in that node, that's the central brain. Okay, so what I've done in this slide and the next one is I've just copied these local neural circuits, so you can see the J0, J1, and the E0 and the E1 circuit down here. It's copied again here, here, and here. So there are 4 copies of that local neural circuit, which are placed in the 4 fins. Make sense? Okay. Okay, so let's talk a little bit about the evolutionary algorithm. We have the genotype to phenotype map now. We have a population of these genotype nested graphs. When we move on to the next generation, we can create new genotypes by mutating existing ones. We can also create them using crossover and grafting. We've seen crossover before, but not grafting. Let's talk about crossover for a moment. So in crossover, what Sims did was to take one genotype graph and to linearize it. Place all of the nodes in the genotype graph in a line. Take the parent genotype graph, put all of those nodes in a line, and now start marching along the nodes in parent 1, and for each node that's visited, copy it into the child. For each node that's copied from the parent into the child, also copy all of the outgoing edges from that node. So we copy this node and this synapse. We copy this node and this synapse. This synapse is dangling because it's not. We only have 2 nodes yet. We don't know what it's attached to. The crossover point is picked at random here. So at this point, one crossover point was picked between node 2 and 3. So we follow the crossover point down to parent 1, and now we start marching along the nodes in the genotype graph corresponding to parent 2. Copy this node, copy its outgoing edge, go to the next one, copy that node and its outgoing edge. We hit another randomly created crossover point. We travel back up, we copy this node, and this node has no outgoing edges. And we fall off the right-hand side of parent 1, and we're done. We spent some time talking about how difficult it is to cross over 2 networks. My guess is most of those crossover events did not lead to very fit creatures, but at least it was in the evolutionary algorithm. Grafting is kind of similar. We again pick 2 parent genotype graphs. We linearize them, start with parent 1, copy all of the nodes and the outgoing edges. We then graft part of parent 2 onto parent 1 by creating an edge. We pick a node at random here. We pick a node at random here. We create an edge between them, which gets copied into the child. We follow that edge to wherever it lands in parent 2 and copy the rest of parent 2 until we fall off the right-hand side of parent 2. Just a different way of combining genetic material from these 2 parents. Okay, so one of the coolest things about the Karl Sims work was what you saw at the end of the video, where they were evolving groups of robots, but in this case they weren't coordinating like the virtual lions we saw last time. They were competing over this common resource, the cube. Out of the population, Sims would draw 2 creatures, and those 2 creatures would then compete for the cube. The creatures had to fit within this starting zone. So if you imagine this 3-dimensional shape here, and the second creature had to fit within this zone here? Why this oblique surface? Why not say the creature just has to start before this line?
It could just evolve to be higher and kind of fall on top of you.
Which is probably exactly what they did. So Sims then said, okay, you have to fit inside of this sloping arena to start, so you can't cheat by falling directly on the cube. Okay, you saw the video of how the robots were competing. You know generally what they're supposed to be doing, which is competing over the cube. What's the fitness function for that? We put two robots in the arena here. They compete over the cube, and we're going to have to compute the fitness of those two robots. What should the fitness, how are you going to compute the fitness for those two robots?
If they're touching the cube, they win. But if no one's touching the cube, the closer.
So if no one is touching the cube, the one that's closer wins, and if one of them is touching the cube, you win. That doesn't quite explain all of the behavior you saw in the video.
It could be whichever robot can get the cube closer to their side of the field.
Could be. That also doesn't explain quite all of the behavior we saw.
Could be both length of time touching and.
Hold on one second. Did you have an idea in the back?
Yeah, I was just gonna say like closest to the center of the body, or like the.
Yeah, that's right. So it's not just to a body part, but get it closer to your center of mass. Yeah, that actually was used. What else? So you're competing here, right?
So for each robot, it could be a combination of adding how close it is to you and subtracting how far away it is from the other person.
Adding how close it is to you and subtracting how far it is, or the other way around, right? Exactly. So the fitness of robot 1 is the fitness of robot 1 is the distance of robot 1 from the target, and there's a negative here. We're trying to minimize D1, right? Get your center of mass as close to the target as possible, and maximize D2. So robot 1 is trying to minimize D1 and maximize D2, and robot 2 is trying to minimize D2 and maximize D1, right? So it's not just about getting as close to the cube as possible, because if you did, you just get a whole bunch of robots that fall or somehow touch the object, right? As long as I'm touching, doesn't really matter, right? That's not quite what you want. You want them to compete. So you're only as good as you do minus how well the other robot does. Dividing by D1 plus D2 just normalizes things. So if we have robot 1 that's 4 units away from the target, and robot 2 that's 8 units away from the target, robot 1 is twice as close as robot 2 is. Those two robots would get exactly the same fitness as another pair of robots where one is 1 unit as close to the target and the other robot is 2 units away, right? That's what they're selecting for. Okay. If you do that, though, if you think about that, we have a population of robots. So they had a population of 300 robots. Are you going to compete every pair of robots, every robot against every other robot in the population? If you do, how many simulations do you need to run? You have 300 robots. You want to compete everyone against every other one. 300 squared, right? 90,000, right? That's at 3 exactly at 3 hours. 3 hours for the population as a whole, because Sims did not do that. Here's all of the different things that Sims tried. So in panel A here, this is all versus all. So we're going to look in the left-hand column first at just one species. So just assuming all the robots can mate with every other one. That's not going to work very well because, again, we have n squared for our population. So let's do something better. Let's do something that at least is more cost-effective. We'll just compete random pairs. What's the problem with that?
You might miss a pair that needs to compete to show which one's better.
Exactly, right? You're getting a number back, a fitness for each member of the pair, but can you rely on that number? If for some reason you happen to compete the best robot against the second best one in the population, the second best robot is going to get a pretty low value. That value might actually be lower than the second worst robot in the population that got lucky because it got paired up with the worst robot in the population. So much faster to simulate B than A, but you can't really rely on that value. So let's try and do something in the middle. Let's do a tournament. March Madness has come and gone, right? Basically the same idea here. What's the problem with this approach? Exactly, right? Or a mediocre team competing against the best team and they get knocked out right at the beginning, right? Bad news for the robots and for basketball teams alike. Same problem. Okay, I think we're out of time for today, so we'll pick up here on Tuesday. You have a quiz due tonight, and your weekly report number 4 is due Monday night. Thank you very much.